Hello, everyone. Today I want to share a very interesting research result. Using only 1,000 carefully selected training samples, a model was trained that can rival OpenAI's s1 preview in mathematical reasoning ability. This research comes from a team consisting of institutions like Stanford University. Recently, OpenAI's s1 model has demonstrated the great potential of test time scaling. Test time scaling refers to improving performance by increasing the computational resources of the model during the inference phase. However, s1 employs large-scale reinforcement learning training, requiring massive amounts of data and computational resources. So, is there a simpler and more efficient way to achieve similar results? The research team proposed an extremely simple but effective solution. First, regarding the data, they carefully selected from 59,000 questions 1,000 high-quality samples, called the S1K dataset. The screening process for these samples was very strict, requiring three important criteria to be met simultaneously. In terms of quality, each sample must contain a complete and clear reasoning process and correct answer. This means not only having the final result, but more importantly, showing how to arrive at this result step by step. These complete chains of reasoning are crucial for training the model to develop good thinking habits. In terms of difficulty, the research team adopted a clever screening method. They had two base models of different scales, 7B and 32B. Solve these problems, by observing the performance of the models, they assessed the difficulty of the problems. If the problem posed sufficient challenge to these base models, it would be retained. This ensures that the difficulty of the training dataset is moderate, neither too simple for the model to learn anything nor too difficult to affect training effectiveness. In terms of diversity, the final selected samples covered 50 different domains. This broad domain coverage ensures that the model can learn various types of reasoning methods, rather than only being good at a specific domain. These domains include basic mathematics, advanced mathematics, physics, chemistry, and many other disciplines. Each domain has its unique reasoning characteristics and problem-solving approaches. In terms of training methods, they adopted the most basic supervised fine-tuning and completed the training in just 26 minutes on 16 H100 GPUs. What is more interesting is the approach to handling during testing. The research team proposed a technique called budget forcing, which is a clever computational resource control scheme. First, the researchers set a computational budget for each reasoning task, measured by the number of tokens. When the number of tokens generated by the model during the reasoning process approaches this budget limit, the system forces the model to stop further thinking and directly provide the final answer. This mechanism prevents the model from consuming excessive resources on a single problem. Secondly, researchers found that the depth of thinking can be regulated by strategically inserting weight instructions during the model's inference process. Each time a weight is inserted, the model is guided to engage in deeper reasoning. For example, when solving complex mathematical problems, the model might re-examine previous calculation steps or attempt to approach the problem from different angles. Experiments have shown that moderately increasing the number of weight instances can significantly improve reasoning accuracy. This approach demonstrates the potential for fine-tuning model behavior through strategic instruction placement. However, it is worth noting that this method of extending thinking time also requires a proper balance. Research has found that if too many weight instructions are inserted, the model may start repeating existing reasoning steps or even get stuck in a loop, rather than generating new effective reasoning. Therefore, finding the appropriate number of weight instructions is crucial for each specific task. This simple method allows the model to recheck answers and correct wrong reasoning steps when needed. Experimental results show that on competition math problems like AIME24, s1-32B achieve an accuracy of 56.7%, while s1 preview achieved 44.6%, a relative improvement of 27%. However, this method also has some limitations. For example, when the model's thinking time is overly extended, it may fall into repetitive loops rather than continue effective reasoning. In addition, this method has mainly been validated on mathematical reasoning tasks, and its effectiveness in other fields remains to be explored. Overall, this study shows us, in the field of large language models, sometimes simple methods combined with carefully designed data can achieve or even exceed the effects of complex methods. This might provide some inspiration for future research. The model, data, and code have all been open sourced on GitHub. Interested friends can try it themselves. That's all for this video. If you found it helpful, please like and subscribe. See you next time.